All right. Well, welcome back, folks. Hopefully, everyone had a good weekend. Hopefully, you had a chance to take advantage of the sunshine over the weekend before we had to deal with the rainy gloom this morning, this afternoon. So that's all right. We need the water. Okay. Um, uh, uh, Quick congratulations to a few of you. For the seniors, will be you'll be done towards the end of this week. Let me. I'll let you know what we'll be doing to finish out here. I won't be giving you a final. My hope, the plan was to kind of finish up with a project for you folks, but obviously that doesn't work anymore. But I'll let you know by the end, by the middle of the week, Wednesday, Thursday, roughly, what you'll be doing. Okay, and so we'll take it from there. Okay, but let's go ahead and let's continue on with where we left off with here on Friday, and we were able to obtain information about the displacement of an object using a velocity time graph, even though I had pointed out to you that we can't determine exact positions for an object with velocity time graphs. We can determine its displacement based upon the areas underneath the velocity time graph. Now we can do this because we saw with the we did the analysis really quickly. Then we saw then that we multiply for example, here we have a constant velocity. Okay, so here we have an object moving at constant velocity. That means that the acceleration is zero. So we did this here. If we take the area underneath the graph here, and the area underneath the graph here is an area swept by this particular rectangle here. If we take the area, then we're basically multiplying length times width here. If we do the analysis of the units for the length times the width, then we obtain then units of displacement, meters, as a result. And so the area underneath a velocity time graph for constant velocity, no acceleration, is going to be that of a rectangle, and therefore we can obtain the displacement from that. Okay? But we can also obtain, so we talked about that, and we worked out this problem on Friday. Okay, but we can also obtain, we said then, the area. We can also obtain the displacement for an object moving at constant non-zero acceleration. Okay, so here we have an object moving at constant non-zero acceleration, meaning that it's constantly changing its velocity. Its velocity is changing, but here we have a changing velocity. Okay, so make sure we. I'm sorry. Let me go ahead. Here we go. Green. Okay. We have that an object that is moving at a constant acceleration. So we can calculate for this, folks, because we can calculate for the slope of this line here. So let's go ahead and do that really quick. Okay, just pick 2 points on the line, and I'm just going to pick let's see, point here at 5 seconds. So I'm going to pick this point here. Okay, so let's pick this point here, which represents the coordinates of 5 meters per second and 2 seconds. Okay, and I'm going to go ahead and go all the way up here to 4 meters per second. Okay, and we'll trace this up here, and we'll get this point here, which has the coordinates of I'm sorry, x, y. So let me go and switch this around. I have that flipped the other way around, sorry. Okay, so it has a coordinate here of, this one is 5 seconds and 2 meters per second, okay? And here then it'd be 10 seconds and 4 meters per second, okay? And so with that said, then let's go ahead and let's work out the acceleration. Remember, the acceleration is going to be a slope between these 2 points here, the slope of the line between those 2 points. And this will be true for this whole thing here because this is constant acceleration. And so I want to do this just to give us some practice in what we did earlier in obtaining information about acceleration from the velocity time graph. So let's go ahead and plug that in. Then we have then 4 meters per second minus 2 meters per second. All over 10 seconds minus 5 seconds. And so we can calculate for the acceleration from the velocity time graph. Then the acceleration here is going to be 2/5 or 0.4 meters per second squared. And that's going to be the acceleration for this whole, for this object here through the whole 15-second time period. Okay, so we can obtain the constant acceleration, we can obtain the acceleration, we can obtain a value for the acceleration from the velocity time graph here. Okay, all right. So with that said, then let me go ahead and erase this. Okay, so that's how we obtain the acceleration there. Okay, what we can do now from this is that let's imagine then we can use the acceleration here to obtain, let's say, final velocity. Okay, so let's go ahead and use this then. Okay, the velocity is changing. The velocity initial here, let's go ahead and do this. The initial velocity here at time 0 is going to be 0 meters per second. We saw then that we can find the final velocity at any other time interval if we know the initial velocity and if we know the acceleration and the time interval that we are going to examine. Okay, so for example, then, if we wanted to find the velocity, I mean, obviously from the velocity time graph, we can obtain this information. We don't need this equation to do so. But remember, this equation here allows us to find the final velocity if we don't have this graph here. Okay, so basically what this formula allows us to do, this equation allows us to do, is to interpolate, which is to find information within the graph that is not plotted on the graph here, or extrapolate, which is to find data points that are outside of the graph itself. Okay, so let's go ahead then and let's use this for equation here and interpolate first and then confirm using our graph here that it is correct. Okay, so let's go ahead then and let's find the velocity at time equal to, let's say, 10 seconds. At time is equal to 10 seconds. Okay, at time is equal to 10 seconds. Let's find the velocity at that time. Okay, which means then the initial velocity, and we're going to base it off of the initial velocity here as being 0 meters per second. But do understand, we can set that initial velocity at any point here. At any point, we could have said that we wanted to start at 5 seconds here and try to find the velocity at 10 seconds. In that case, then the velocity then initial would be 2 meters per second. Okay, so make sure you keep that in mind. But just to keep things simple, we're going to say then that the initial velocity is going to be at the initial time, which is going to be time equal to 0. Okay? All right, plus here's our acceleration. Our acceleration we just solved for, that's the slope of the line here, which is going to be 0.4 meters per second, all over the time interval here, which is going to be 10 seconds. Okay, and so we plug that in then, we're going to find then that the final velocity at 10 seconds here, final velocity at 10 seconds is 4 meters per second. And if we follow this on the line, then if we trace the line, and I'm just going to go and do this really quickly, from 10 seconds here, we trace it up to the graph here. Okay, there it is, and then we trace it over, and there we have it. We have confirmation then that the final velocity, the velocity at 10 seconds, is going to be 4 meters per second. Okay. All right, so let's go ahead and do one more. Let's do one more. Let's say then we want to find the velocity at 15 seconds. Okay, we want to find the final velocity at 15 seconds. Let's go ahead and do that. We have final velocity then. It's going to be equal to initial velocity, which again is going to be 0 meters per second. Acceleration is constant still, so it's going to be 0.4 meters per second squared. This time, though, the time interval is a 15-second time interval. And so we plug that in, folks, and I'll let you go ahead and do that. Okay. We end up with an answer that is going to be 6 meters per second. Okay, which is, if we follow again the graph here. Okay, so at the time is equal to 15 seconds here. Okay, we trace our line up. Oops, sorry. Go do this here. Not working. We trace our line up to the graph. Okay. And then we trace it over to the y-axis, and there it is, 6 seconds. Okay, so we have then confirmation from the graph itself that we can find final velocities if we know the time interval. So for example, let's say we wanted to find, okay, so now we're going to extrapolate because 20 seconds is not included on this graph. The graph here ends, the time interval ends at 15 seconds. But since we have this formula now, we can go ahead and we can find the time then, the velocity at 20 seconds by plugging it into the equation here. Again, initial velocity is going to be 0, okay, 0.4 meters per second squared. And this time, though, we have it at 20 seconds. So let's go ahead and plug that into your calculator. Sorry, plug that into your calculator, and let's get the answer here. 20 times 0.4. We have then 8 meters per second. Okay. And so this point here, folks, lies well outside of the time and well outside of the velocity. So this time here and this velocity here lies outside. So what we've done here is we have extrapolated the information from the graph. And again, you could easily have extended this line here. You could have stretched out this line and you could have gotten this from the graph, but we can easily get it from using this equation right here. Okay, so that's the reason why equations are much more useful than graphs. Graphs are excellent, but it's cumbersome. Okay. All right, very good. But that was just a review. That's not what we're after here, folks. What we want to be able to do is we want to be able to find the distance that the object travels here. Okay, so we want to find then how far with the total displacement that the object travels, okay, as it goes from 0 to 15 seconds, but it's changing its velocity as it does so. Okay, and so with that said, then we can with the constant velocity, that is acceleration is 0. That was easy. Find the area underneath the rectangle. With this changing velocity, the method doesn't change. What we use does change though, because here now the area underneath this curve is a triangle, and so therefore to find this area we'll need to use the formula for the triangle, which is 1/2 base times height. Okay. All right, so with that said, then our total base here then is going to be the total time, which is going to be 15 seconds here. So therefore, the base is going to be equal to 15 seconds. Okay? And so the height here is going to be this height right here, folks. So the total height, which is the final velocity here, and that's going to be then the velocity here, the height then is going to be 6 meters per second. So even though the velocity does change, we're going to use the final velocity here at 15 seconds in order to find the total distance that it travels. Okay? All right. So with that said, then I think the formula becomes very simple. Okay? The calculation becomes very simple. It's going to be 1/2 base, which is going to be 15 seconds, times the height, which is going to be 6 meters per second. If you do the unit analysis here, folks, if you notice that the seconds cancel out, and so you end up with a I'm sorry, 45 meters, okay, as your total displacement. Okay. All right, very good. So from this one problem, we were able, actually the only question that you needed to answer is the last one, the third calculation. Okay, but hopefully make sure you write this down, folks, because it allows us to review what we've learned about graphing, about acceleration, about velocity time graphs. And so the first 2 calculations we did here, we did initially. Okay, we learned this early on when we were talking about velocity time graphs, talking about acceleration. Okay, and so with that said, then this here allows us now to determine the displacement. Now understand this, folks. We know how far it traveled. We know how far this particular object traveled. What we do not know is the exact starting position and the end position. We just know that it traveled some total distance of 45 meters. Okay? And so we still are not able to obtain exact position information from the graph, but we do know how far the object traveled now. Okay? So please make sure you keep that in mind as we go through with this. Okay? All right, so with that said, let's go ahead and let's do the last one. Let's do the next one. Okay? And let's work this one out. What I would like you to do is I would like you to do the same thing here. I would like you to do the same thing that I did early on the previous slide here. I want you to find the acceleration. So let's go ahead and do this here. I want you to, first of all, find the acceleration for this object. Find the acceleration from the graph. Okay. Let's go ahead then and find, secondly, I want you to find V final. What's the final velocity? And at time is equal to 15 seconds. So go ahead and we'll work that one out. And then we'll go ahead and we'll solve for the displacement in just a moment. Okay, so go ahead, work those two out. Take about 2 to 3 minutes. I don't think it should take too long. 2 to 3 minutes to work out those two. And then we'll go ahead and work those out together. Again, this is just practice. We'll work this out together. And then we'll find the displacement. Okay. All right. Go ahead and get that done. All right, folks. So let's go ahead and let's find the acceleration first. Let's go ahead and work out the acceleration first. Let's find this one. Okay. And then we'll find t is equal to 15 seconds. Okay. So velocity at time is equal to 15 seconds, and we'll solve that in just a moment. All right, so let's go ahead then, and let's just find 2 points on this graph here. I'm going to go ahead and pick the 2 easiest points here at the beginning and at the end. Okay, and so the coordinates here at the beginning then is going to be 0 seconds and 4 meters per second, x and y coordinates. The final point here has the coordinates of 15 seconds and 0 meters per second. Okay, so plugging that in, then we have then v final, that's going to be 0 meters per second minus initial here, which is 4 meters per second, all over the change in time, which is going to be 15 seconds minus 0 seconds. Okay, and so when you plug that in, then you're going to get an acceleration that is going to be negative, and it's going to be 0.267 with the 6 repeating meters per second squared. Okay, so there is your acceleration. Okay, that's your acceleration. It's constant acceleration. Now make sure you keep in mind the acceleration here is negative. All the velocities along this line here will be positive, and so if you take a look at just the signs, you'll notice that the object's going to be slowing down. But you can obtain that from the graph, folks. So you can get that information from the graph as well. Okay, so that's no biggie. Okay. All right, so let's go ahead then and answer the second question. Let's talk about V final. Let's calculate for V final at the time is equal to 15 seconds. Okay, so plugging that in. The initial here, folks, is going to be 4 meters per second. Okay, so the initial here, it's going to be 4 meters per second taken at time 0, plus the acceleration, which we just solved for here. This is constant, non-zero acceleration. Negative does not mean less than 0 acceleration. Make sure you keep that in mind, folks. Negative just means then the direction that the acceleration is in, which is in the opposite direction of the velocity. Okay? Again, the object is not moving in the negative direction. It's still moving along the positive direction. It has a negative acceleration because it's slowing down. Okay? All right, so with that said, then let's plug that in. This is going to be negative 0.267 meters per second squared, or if you want to write this down, 4/15, negative 4/15, because that'll make it work out a little bit easier for you, times 15 seconds, which is the time interval. And if you use the fraction here, 4/15, the 15s will cancel out. And so you'll find then that this will give you 4. Okay, and so the final velocity here, which we get confirmation of with from the graph, it's going to be 0 meters per second. Okay, that'll be your V final at 15 seconds. Okay, all right, very good. Let's go ahead then and let's solve for this problem here. And so the displacement then is going to be the area underneath this triangle right here. So the area underneath the triangle then is going to be 1/2 base times height. Okay, the base here then, we'll take the base then as being 15 seconds. Okay, so the total base is going to be 15 seconds. The height here will still be 4 meters per second. So again, we're taking the total length here. Okay, so therefore it's going to be 1/2 base 15 seconds times height, which is 4 meters per second. Okay, and so we get a total displacement then of 30 meters. Okay. All right, so that's how we would go about calculating using the graphs here. Graphs are very useful, folks. Make sure we get used to using the graphs here and obtaining information from the graph itself. Okay. All right, let's move forward though. Let's move on and let's take a look at what we have here. What if we have both constant acceleration and changing acceleration at the same time? Because this is how most objects move. Most objects are not always moving at a constant acceleration. Okay? I'm sorry, they change their acceleration as well. Okay? And so what we have here, so most objects, they will move at a constant velocity for a little time period interval, and then they will speed up or slow down over a certain time interval. And so most motion depicted over a large period of time, we would say almost all motion, is not always going to be constant. It's not going to be constant 0, or it's not going to be constant changing as either. Okay? So in both cases here, we have constant acceleration. Okay? In this first case here, the acceleration then is going to be 0. Okay? It's going to be 0 meters per second in this particular region here. And in this particular region here, we have an acceleration that is not equal to 0 meters per second squared. So we have 2 situations, and this is how this graph will allow us to kind of approximate how most objects move. And so under these circumstances then, how do we find the displacement? How do we find the displacement of an object that is changing it's changing its velocity and then settling in and moving at a constant velocity. Okay? So this is what we have to examine next. This is what, again, this is what happens in real life. Okay? Objects will not always move at a constant velocity. They will change their velocities, and then they can also move at a constant velocity as well. Okay? All right, so let's go ahead then and let's consider what we have here. Okay, so if we're going to find the total displacement, okay, let's imagine this here, and I'm going to go ahead and write this in as such. Okay, so we would have to consider then two displacements. Displacement number one, displacement number one here, I'll call this displacement number one, and this will be displacement number two. The object is undergoing two different types of displacement. The object is undergoing two different types of displacement. Displacement at constant zero acceleration and displacement at constant non-zero acceleration. However, so with that said then, if we take a look at this, you can imagine then that if you look at the picture to find the total displacement, remember to find displacement, we just want to find the area underneath the curve. So the area underneath this curve is comprised, underneath this curve here, which is this line and this line right here, is going to be comprised of this area here, which we'll call area one. It's going to be of the rectangle. It's going to be length times width. And this area here, which we'll call area two, that's going to be 1/2 base times height. So this is the area for the first triangle. This is the area for the second triangle. And so if you can imagine this then, to find the total displacement, okay, we would have to find then the displacement from the constant zero acceleration, and we're going to add that to the displacement for the constant non-zero acceleration, which means then, if we look at this then, we would add together the area for the rectangle plus the area for the triangle. That is how we will find the total displacement, okay, using graphs here. Okay, so keep that in mind as we work through this. Okay, so let's go ahead then and let's work through this together. Okay, let's go ahead and work through this. Okay, all right. So we said then, let's go ahead and let me go ahead and. Okay, so we said then that we want to define the total displacement. We need to find the displacement for area one and add it to the displacement for area two. Okay, which means then this will be area one plus area two. And that's how we find the total displacement. Okay. All right. So let's go ahead and consider area one. Area one then is going to be velocity. So it's going to be y, base times height, length times width. Okay, so that's going to be then, let's go ahead and plug this in. I have it written out here for you. This is going to be then velocity times time. The velocity doesn't change, folks. The velocity doesn't change, so it's going to be velocity over the time interval that it moves at that constant velocity. Area two is going to be 1/2 here. So remember, this is area two for our triangle. This is going to be 1/2 base, which is going to be time, times height, which is going to be velocity. So we'll write that in as the change in velocity here. Okay, so the velocity is going to change. Okay? The change in velocity times time. Okay, so that's what we have right there. So far we have our equation that we can use in order to find constant the displacement. Okay. Now what I'm going to do here real quickly then is that we know this. Okay, let me just go right to the side here. We know then that acceleration is equal to the change in velocity over a given time interval. Okay, so we know that about acceleration. Just quickly rearranging this equation here. We're going to rearrange this equation to solve for delta V, change in velocity, which means we multiply both sides by time. We get then delta V then is going to be acceleration times time. Okay. All right, so again, all I did was took the equation for acceleration and multiplied both sides by time. Why did we want to do that? Because folks, look, if we can take this here, because delta V, this here is equal to AT, we can substitute that in right here. Okay, so let's go ahead and let's take this part right here and substitute it in right there since it's equal. Okay, so if any part of this you're not quite sure about, make sure you come by and see me. Because if we do that, and there's a reason why we're doing that, okay, if we do that, we can find then that delta, the total displacement then is going to be equal to the velocity for the time interval that this object moves at constant velocity, plus 1/2, let's substitute this in, AT, sorry, A, acceleration times time, times T again out here, okay? So we get that. Let's simplify this one last time then. And so if we simplify this, then we have delta X displacement is going to be equal to VT plus 1/2 AT squared. Okay. Once we set it up that way, folks, this gives us then the second of our kinematic equations, okay, which allows us to solve for displacement, if we know velocity, okay, if we know the velocity at the constant that is constant, okay, the section portion of the motion that is constant, okay, we can identify the velocity and we can identify the acceleration, okay, the constant acceleration, okay. So we need to find constant velocity, constant acceleration, and the total time interval over which that object moves. So the total time interval over which that object moves. And so if we can obtain that, if we can get that information, if the problem gives us that information, we can find for the displacement. Okay, so this is the second kinematic equation. Okay, remember the very first one that we learned about was just taking the formula for acceleration and solving for it. So the very first one we learned, and we've used already this morning, this afternoon, to solve for final velocity, this one. Okay, so we now have two kinematic equations that we can use to solve for motion. Okay, so this is the very first one. We just solved for this one. We're going to do, I'm going to introduce one more to you, and we can use the kinematic equations. And remember to find motion, to describe the motion of an object that's moving with a constant acceleration. Okay, all right. So let's go ahead and let's take a look at a problem that would require us to use one of these two equations here. Okay, so let's go ahead then and let's take a look at a problem and work that one out together. Okay? All right, so with that said, that's what we have right here. So based on this, if we know the initial position, folks, we can find the final position. Okay, so this is the equation I just worked out for you. Okay, so let's go ahead and what you want to keep this in mind then. This equation will give us displacement. This equation will give us displacement if we know the velocity initial, the velocity of an object that's moving during the portion that it is moving at a constant velocity, and when it starts to change that velocity. Okay, so you have the velocity initial, and then you have to tell the velocity that's moving at a constant velocity, and then when it changes that velocity, that's what the acceleration is there to remind us of. Okay, all right. So what we don't need here, folks, so if we don't know anything about the final velocity, we can still use this to find the displacement. Okay, all right. And so and with this equation here, if you notice that we cannot obtain final velocities either. Okay, so if final velocity is not mentioned in the problem, you're not asked to solve for it, it's not given to you, this is the equation we can use to find displacement. Okay. All right, let's take a look at an example. Take a look at an example here. Okay. We have a person moving here, and let's go ahead and identify what we're given. Okay, we have a person that's moving. Okay. We're told then that the this object here, Sikazi, has a constant acceleration. So we have a constant acceleration here. Okay, so we have a constant acceleration mentioned. So we have an acceleration of 0.5 meters per second squared. Okay, so we have that. That's taken from the problem here. Okay, and then what we see then is once the push is done and the acceleration is there's no more acceleration. Okay, then the object Sikazi moves at continues to move at a constant rate of 3 meters per second. So there is the constant velocity of 3 meters per second. Okay, and so so this is done for a total of 6 seconds. Okay, this is done for a total of 6 seconds. Okay, so the time interval here is 6 seconds. Okay, and so we want to be able to use this in order to solve. And so 6 seconds. Okay, and that's the time interval here. Okay, all right. So with that said, then let's go ahead and let's with that information, let's find then they asked then for the displacement, and I'm running a little low on time here. Okay, so find the displacement for this particular object. Okay, let's go ahead then and let's plug it in and solve for it. Okay, all right, and So you can imagine here then, we have a constant acceleration, constant motion at for 3 meters per second, and the acceleration here for point 0.50 for another 6 seconds. Okay. All right, so let's go ahead and let's plug it in and let's solve for what we have. Okay, so let's go ahead and I want to bear with me a little bit more folks, and then I'll finish up here. Okay. So we have then we want to find displacement, and hopefully you had it written from the previous slide here, what we have here. Okay, so we have then the object moving at constant velocity for a given time interval, okay, plus the acceleration for another time, for that time interval, 6 seconds as well, okay? So it's, at this point, folks, it's plug and chug. So we have the initial velocity, I'm sorry, the velocity that is moving at a constant velocity. We're told then that's going to be 3. He moves at a constant velocity of 3 meters per second for a total of 6 seconds. Okay. And then we are told then that he accelerated, his dad pushed him, he's for a constant acceleration of 0.5 meters per second squared, also for a 6-second time interval. So you plug that into your calculator, folks, you're going to get your answer then as being total displacement then as 27 meters. Okay. So working out these problems become very simple. You just have to be able to recognize when you have to use this particular equation. Okay. All right. So with that said, then please make sure you you work this problem. What I'd like you to do right now is let's take a look at this problem right here. Okay. And I would like you to work through this problem to finish up with. So and we'll start this problem tomorrow. Okay. So work out this problem to finish up with, and then have it with you for tomorrow. Okay, and then we'll work out this problem together. And then we're going to continue on to the third last of the kinematic equations. I want to introduce that to you. We won't derive that equation. It's not that difficult, but it's a little bit more involved. So I don't want to derive that equation for you, but I will introduce it to you, and we'll talk about how and when we use it. Okay. So please work out this problem here. Have it for tomorrow. Submit it today, and have it for tomorrow, and then we'll work out this problem together. Okay. All right, folks. Very good. I will have a good day, and I will see you tomorrow.